Hello students, welcome to a video about combining bases. This is the last rule that we're going to learn about exponents, and it explores what happens when we have two powers that are being multiplied or divided or a power to a power or whatever, but the bases are not the same. In every case we've looked at so far, it's been, for example, 10 to the power of 2 times 10 to the power of 5 or something. So what happens when the bases are not the same? For a little warm-up, I want you to answer these two questions. Go ahead and pause your video and evaluate. That doesn't mean write it with an exponent. That means actually go through and solve and give me a single number that is equivalent to each of these things. Go ahead and do that now. Okay, so 5 to the power of 3 times 2 to the power of 3. We can use our expansion method, writing in expanded form, to realize that this actually means 5 times 5 times 5 times, here we have 2 to the power of 3, so that's 2 times 2 times 2. So we can just go through, there are a million ways to work through this, but if you just read it from left to right, that would work. 5 times 5 is 25. 25 times 5 is 125. Times 2 is 250, times 2 is 500, and times 2 again is 1,000. Got there eventually. 1,000. There are actually easier ways to do that I would have preferred, but we'll look at those in a second. The second one, 10 to the power of 3, that one's a little more straightforward. That just means 10 times 10 times 10. 10 times 10 is 100. Times 10 again would be 1,000. Wow, I wonder if that's a coincidence that we got the same answer for both questions. It's not a coincidence. Let's look at the next example and you'll see what I mean. We've got a table for you to, I know that this is a video so you can't really fill it out, but kind of work along with me. I'm gonna do the first one for you and then we'll work through the next ones, and I'll give you time to pause and think. So we have an expression of 3 to the power of 2 times 7 to the power of 2. We want to write that first in expanded form. 3 squared just means 3 times 3. Actually, I'm going to write this a little smaller right here. 3 times 3 times 7 squared, which is 7 times 7. Now, we are only multiplying in this expression. There's no addition, no subtraction. So because we're only multiplying, we can use the commutative property to do that in any order that we want. So I could rewrite this as 3 times 7 times 3 times 7. There's still 2 3s, there's still 2 7s. This means the same thing. But now if you notice, I have them in two groups where each group has the same product. We have a 3 times 7 in one, and we have a 3 times 7 in the other. So couldn't you say we have 3 times 7, whatever that is squared? We'll do that on this next line. 3 times 7 is 21, right? So we really have 21 times 21. You could go through and do that on a calculator, but we're looking for the exponent. We want a single exponent. We have 21 twice. So that's 21 squared. Now look at the original expression and see if you could come up with a rule that would take you from that expression to the finished exponent. If you can't come up with a rule right away, that's fine. We'll do a few examples, but I think some of you will be able to tell immediately how this works. Go ahead and try the next one. Pause your video and see if you can do that on your own. All right, I'll go ahead with this one. 2 to the power of 4 is 2 times 2 times 2 times 2 times 3 to the power of 4. 3 times 3 times 3 times 3. So we did 2 4 times and 3 4 times. Now again, let's try to match them into groups so that we have a bunch of the same group repeated. How about 2 times 3, that could be a group, times 2 times 3 times 2 times 3 times 2 times 3. So all I did was just match them up together so that each set of parentheses contains the same thing. 2 times 3 is 6. So what we have is 6 times 6 times 6 times 6. In exponent form, our base is 6, and our exponent is however many 6's were being multiplied, which in this case is 4. Again, look at the original expression, compare that to the finished single exponent. Can you see a pattern? Can you see a rule that you could use on the next one? Okay, the next one I'll do in orange. 7 cubed, 7 times 7 times 7 times 2 cubed, 2 times 2 times 2 times 5 cubed, 5 times 5 times 5. This is a lot of numbers. I don't really feel like going through and writing them all out in pairs. Actually, this time it would be in groups of 3, right? Each parenthesis would have to have a 7 and a 2 and a 5. But I think we could just go back and notice the rule that we've seen and see if we can use that in this case. If you notice in this example, 2 to the 4th times 3 to the 4th equals 6 to the 4th. One thing changed, one thing stayed the same. The base of 6 is new. How do you get a 6 from a 2 and a 3? Multiply. So this says when you multiply two numbers with the same base, when you multiply two numbers with different bases, you multiply their base. 2 times 3 is 6. The exponent used to be 4 in each of them, and it's still 4. It didn't change. So if we look at this new example, we have 3 powers that all have different bases, but notice they all have the same exponent. So let's just multiply these 3 numbers together and leave the exponent. 7 times 2 is 14. 14 times 5, let's see, 10 times 5 is 50. 4 times 5 is 20. Add those together, we get 70. So we would end up with 70 to the power of 3. We left the exponent, we multiplied the bases together. That's the rule for, well, actually, we'll write the rule in the next line here so you can see it really clearly. A to the power of n times b to the power of n. Bases are not the same. Exponents are the same. When that happens, multiply the bases and leave the exponent. So if I multiplied the bases here, I'd have a times b, and the exponent just stays the same, n. That technically would go over here. ab to the power of n. Okay, let's try our next one. Select all the true statements. See if you can just pause your video and see out of these 4 equations how many of them are true. Go ahead. Okay, first one, we're multiplying with the same base, so we add the exponents. We should have 2 to the power of 17. That one works out just fine. B, we do not have the same base, so we're using our new rule. We don't have the same base, we do have the same exponent, so we'll leave the exponent. It should be 2, which it is, and we should multiply the bases. 8 times 9, which is 72. That one works out as well. C, we have 8 squared times 9 squared. We do not have the same base, but we do have the same exponent, so we can use our new rule. Leave the exponent. It should be 2. Our right side of the equation does not have an exponent of 2, it has an exponent of 4, which doesn't follow our rule, so that one does not work. And D, 2 to the power of 8 times 2 to the power of 9. We have the same base, and we're multiplying, so we add the exponents together. 8 plus 9 is 17. That's correct. But we're supposed to leave the base the same. The base here should be 2, not 4. So that one is not correct. And our last activity for this video, find the missing exponents. I have little pink squares here. A number should be assigned in each of those squares that's equivalent to this expression. Go ahead and pause your video and see if you can find what those numbers are. Okay. In order to explain this one, I'm not going to actually I could write out 3 times 5 times 3 times 5 times 3 times 5 times 3 times 5, because that's 3 times 5 4 times. And then I would do the same thing with 2 times 3, 5. It will just take way too long. But an easier way to think about this is, over here we have 2 to the power of something. So how many 2's? How many 2's were there on the left side of this equal sign? Well, there are no 2's here. Here's a 2, and I know that it is being multiplied by itself 5 times. Here's a 2, and I know it's being multiplied by itself 7 times. So if there are 5 2's here, 7 2's here, that means we have a total of 12 2's. So that should be raised to the power of 12. 3, how many 3's do we have? Well, here's a 3 which is being multiplied by itself 4 times. Here's a 3 that's being multiplied by itself 5 times. 4 and 5, we are at 9. 3 is being multiplied by itself 9 times. And finally, the number 5. Here we have a 5 being multiplied by itself 4 times. There are no 5's in this expression. Here's a 5 being multiplied by itself 7 times. 4 times and then 7 times, we'll add those together, and we have 11 5's being multiplied together. So those are your finished exponents, 12, 9, and 11. If I were to just have written all of these out in expanded form, you could have just gone through and counted 12 2's, 9 3's, and 11 5's in that list. Hope that helps. Hop on MathSpace and get some practice done. You're amazing.